Okay, so I'm going to do a quick drills part 2 where I'm going to talk a little bit about some of the things that I skipped over just because I can. So, we didn't talk about micro drills. Now, the reason I left out micro drills is that they don't really follow the same rules as standard dimension drills. Most of the time, we'll split micro drills into two main categories. We're going to talk general purpose carbide and we're going to talk high performance carbide. General purpose carbide on micro drills are going to be your printed circuit board drills, PCB. You'll find those through several different brands, and they are going to be somewhere between 300 and 400 thousandths length of cut, so 0.300, 0.400. And their diameter will be under 1/8 always, because that's what makes them a micro drill. And so those will come coated or uncoated, and depending on what material your customer is working with, you'll make that decision. Again, basically, it breaks down to, I'll talk in a little bit bigger terms in this one. In non-ferrous materials, aluminum, brass, things like that, you want it as sharp as possible. You don't want any coating, especially not like the standard TIALN or ALTIN, Alton-Thailand coatings. Those contain aluminum. When the aluminum in your coating heats up, it will stick to the aluminum that you're cutting and give you trouble. And you don't want that. So they're going to be between 300 and 400 length cut. And the other thing is that micro drills almost always have a reinforced shank. Carbide micro drills have a reinforced shank. And high speed and cobalt, they tend to be straight shank, which means like for a 70 thou drill, it would be a 70 thou shank, straight shank. But a reinforced shank, generally on micro drills, it's going to be 1/8 of an inch, sometimes 3 millimeter if you're talking metric. And that's just because those are really standard, and it adds some, I guess I want to say rigidity. Is that that sounds like the right word? Because it gives you more to hold on to, right? Because carbide is kind of I don't want to say brittle, but that's the closest word I can think of. Carbide is it's much easier to accidentally snap a piece of carbide than it is to accidentally snap a piece of cobalt. Even though carbide is generally stronger, it doesn't do well with bending. And so one of the ways that you can reduce that, like the vibration and the bending, is by having that reinforced shank. And then we're going to talk about high performance micro drills. And when I say high performance, I'm talking about like a Mitsubishi, or maybe like a Kyocera had some good ones for a while. Walter, you name it. But like when we're talking high performance drills, those have a lot more options as far as the length of cut goes. And as you get into longer lengths of cut, you'll tend to also get through coolant on some of them, which I touched on before. And so those, they don't go by stubby or jobber. You know, you're going to pull out your catalog. The customer's going to say, well, I need a 70 thousandths drill, and I'm going however deep, right? And you're just going to go through the catalog, and you're going to match up the LCF, length of cutting flute, with their depth of their hole. So let's say it's a 70 thou drill, and their hole is 800 deep. You're going to do some math, or you can actually just compare and know that you need a drill that's at least 12 times as long as it is wide, so 12 times D, to drill a hole that deep. So you'll just match that up, check the material, and you're done. That's micro drills. And then the other thing I wanted to talk about that I said I wasn't going to were super long drills. And that's also pretty basic. It's going to be the same basic idea. So instead of it being stub or jobber, they're going to say, well, it's got to go like, it's a 1/4 inch drill, and I've got to drill 2.5 inches deep, which is, on something like that, you always, on a carbide drill, you always want to have through spindle coolant running. Otherwise, the chips will build up in your hole, and you'll snap the drill, right? Because you got to think, the deeper you go into the hole, the harder it is to get the stuff that you're cutting at the tip of the drill all the way out of the hole. Just, it's like inherently harder, right? The more distance you have to travel. So the trick is through spindle coolant. It's literally like if there was water coming towards you, because it's pushing the chips out. So like through spindle coolant on longer drills is critical, because you can't, long carbide drills aren't designed for pecking, which pecking is, and slowly getting deeper every time, right? You just kind of, like carbide drills, most high performance carbide drills are designed to poke straight in and come straight out. And the way you achieve that is by blasting your coolant down and evacuating the ships rapidly, as opposed to the pecking method where you go in, drill a little bit, take the drill all the way out, and then go in and drill a little bit. The reason you don't want to peck with a carbide drill is, like I said before, is it's very easy to snap a carbide drill. And so if you end up misaligned in your hole when you go back in, or any sort of issue, and you're reducing your tool life. So it's just generally not something you want. Also, carbide tools tend to do better with like a steady engagement versus an interrupted cut, which I am not going to talk about right now. But yeah, so those are the things I skipped over, and as you can see, that took longer than the whole video on everything else about drills. But yeah, I hope that this was a little bit more insightful.